Okay, in the last video, you saw that we used this new terminology to discuss the area beneath the curve. We used what's called the definite integral. And all that really is the use of the integration symbol with a couple of new components. We use limits of integration. And they're not limits like LIM limits. They're a starting point and a stopping point. And the integration symbol that looks like an S, the S stands for sum or sweep, because we're sweeping out a continuous area beneath the curve. Now, we haven't used calculus to compute those areas yet. We just use the terminology to represent that that's what we're looking for. So if you want to represent the area beneath the curve, we use the integral symbol with a starting and stopping limit of integration, then the function, and then dx or ds or dt, whatever the independent variable is. Now, up until now, to actually compute the area, we either use a geometrical formula for like the area of a circle or a semicircle, or we use the limit method of finding the area beneath a curve. That's with the limit, the sigma, the delta x. That can find the area beneath any curve. Now, if the curve happens to match a circle or a triangle or something, or a trapezoid, then we can also use a geometric formula to compute the area as well. So I want to talk about section 4.4, which has a very important notion, and that is the fundamental theorem of calculus, which sounds pretty important, and it is pretty important. And it really relates that new symbology of using the integration symbol, the definite integral we call it, with limits of integration, and finally makes the connection and allows us now to find the area beneath the curve, not using the limit method, not using a geometric formula, but instead using calculus, which is generally going to be a lot quicker. So the fundamental theorem of calculus, before we get to it, I got to remind you that we have done antiderivatives. We use the integration symbol, and the integration symbol says what is the original function whose derivative is lowercase f of x. Don't forget, dx is always has to be there. It's a reminder of the independent variable x. Now, if this was a function of t, this would be dt. The noun antiderivative is produced over here because we're answering this question. What is the original function whose derivative is this right here? And this is it. Now, to get that function, we need to use our rules, which are like the power rule and things like that, the constant multiple rule. Sums and differences are easy as well. And then also we have this item in the back called the constant of integration. So when you do an indefinite integral, that's what this is called, you always want to put plus c in the end there. And the reason is because there could have been a constant, but you just don't know what it was because the act of taking the derivative would make the constant vanish. Therefore, we don't know what it was, but we know that it might have been there. The verb is to integrate or anti-differentiate, and that's what the integral symbol does for us. All right, in addition to learning about the antiderivative and integration, we also discussed finding the area beneath the curve. And the way we did that was we sliced the curve up using rectangles. But the ultimate best answer, the most accurate answer, is to make these rectangles hair thin as possible. And when they are as thin as possible, in fact, delta x goes to 0, then we can fit an infinite number of them underneath here, and that would give us the most accurate area under the curve rather than an approximation. So what did that look like? Well, this was the summation formula that gave us the area beneath the curve, and let's piece this together. Each rectangle has a height and a width. The height is a y value, of course, and the width is a little bit of x, delta x. The sigma is there to add them all together, so that we add each rectangle to the next one. And how many rectangles ultimately do we want? The best answer is when we have an infinite number of them. So n approaches infinity, and while n approaches infinity, delta x also approaches 0. The width has to get really thin in order to fit that many underneath that rectangle. There's a strong connection between the sigma version of finding area and the definite integral of finding area. We call this a definite integral. So the definite integral has an integration symbol, so it does kind of command us to anti-differentiate. The height is still there. F of x is the height. The width is still there, but delta x becomes a dx. So what does dx represent? Dx represents our old width of our rectangles, but dx is the thinnest possible width that we can imagine. So delta x is going to 0, but you know what? It never quite makes it there. N is going to infinity, but you know what? It never quite makes it there. So what does delta x become? Delta x becomes dx, and it's not 0. It's as close to 0 as you possibly can imagine, and that's what it represents in our definite integral. Now, the fundamental theorem of calculus states the following. Not only do we have a representation of area that is a definite integral that looks like this, and we've done this before. We've used this terminology in the previous section. We haven't done any calculus on it, but we've said the area can be represented by integrate from a to b underneath the function dx. But we've found the area using different methods. But now we can find the area using calculus. Now, I do have a little problem using calculus directly on this, because if I do and I anti-differentiate, you know what happens, right? When you integrate this function, you produce another function. You actually discover capital F of x. So it says to me, I'm thinking of an original function. Whose derivative is this? And there's the answer to that question. And we can use all the rules at our disposal to get that answer. But my problem is capital F of x is not an area. Capital F of x is a function of x. That's like saying the area beneath the curve is secant or tangent or something like that. The reality is the area under the curve is 12 or 15 or -7 or something like that. So how do we change this into a number? And the way we change that into a number is by copying the limits of integration over on the right side here. So yes, you produce capital F of x like we did before with indefinite integration, but there's more to it than that. You actually need to plug in the b into your function and plug in the a into your function. And when you do, you're going to get numbers. So this indeed is the fundamental theorem of calculus, and that is that you can use calculus to find the area beneath the curve by first finding the antiderivative. That's the first thing that we're going to find. And then you literally plug in the limits of integration. So we would do capital F of b, which is the stopping point, minus the capital F of a. Don't do lowercase here, because if you do lowercase f minus lowercase f, all you're doing is subtracting two y values. That really has little to do with area. You need capital F. You need the antiderivative in order to really do this. Okay. What I'd like to do next is I'd love to find the area beneath a curve that we've already worked on, specifically this one. We've done 4 minus x squared before, and the way we've done it is we've used the limit method. We've worked through the limit method. Actually, before we used the limit method, we approximated the area into this curve with an over and under estimate, and then we split the difference. Now, the approximate area was 5 1/4, and then we ran the limit method and got the exact answer, which was 5 1/3. Now, the terminology that we have for area beneath the curve is now this, the definite integral. The S looks like sum. The S looks like sweep, because that's what we're doing. We're sweeping out these hair-thin rectangles, continuously summing and accumulating area. The height of each rectangle is the y value at that location. The width of each rectangle is dx, dx being the thinnest possible slice of x you can imagine. Now, our function is 4 minus x squared, so we're going to put that in behind the integral here. And now for the first time, we can break this up and do calculus. So let's integrate 4 all by itself. Let's integrate x squared all by itself. Before we do that, let's not forget that constant multipliers can come out front. So let's park that constant multiple out front. 4 comes out, and then x squared, you can't take that out front. You have to work on it. But notice that by taking the 4 out front, we have antiderivative and derivative canceling each other, which is a good thing. Whenever they touch, they literally cancel each other out. What's next? Well, the 4 isn't going anywhere. These cancel each other out. They're opposite operations. If they touch, they do anyway. And I get the letter x. In other words, the antiderivative of 1 is x. The derivative of x is 1. That makes sense. And don't forget, it produces a constant of integration. Over here, if you integrate x squared, look what happens. Add 1 to the exponent, divide by the new exponent, and you also produce a different constant of integration, c2. Now, that's not area. That's got x's in it and c's in it, and I need a numerical area beneath the curve, which we already know the answer to, 5 1/3. So how do we get there? We get there by plugging in our limits of integration. So starting with the 2. The 2 goes in, you plug it in, you get 8 plus c1 minus, and then you put the 0 in, 0 plus c1. So that 0 doesn't contribute all that much. Over here, x cubed over 3, we plug the 2 in first, and we get 8/3 plus c2. We plug the 0 in, minus, we get 0 plus c2. So again, where's this minus coming from? It's not coming from here. It's not coming from here. It's not coming from here. It's coming from the fundamental theorem of calculus. So the fundamental theorem of calculus says if you want to turn your antiderivative into an area, you plug the b into your function minus you plug the a into your function. And that's truly what I'm doing here. That's where that's coming from. All right, let's take a look at where we're at on this problem. So notice something. C1 minus C1, they canceled right out. Now let's propagate this minus through 8/3. Minus hits the C2, and a minus, and a minus, and a plus make a plus C2. Notice that the constants of integration cancel themselves right out. So finally, we land on our numbers. The area beneath this curve is 8 minus 8/3, which is 24/3 minus 8/3, which is 16/3. 16/3, that's 5 1/3. So we did get our result, the same result we got by integrating or getting the area under the curve using the limit method, which is the hard way. This is much easier using calculus. I'd like to try this again, and I like sticking with functions that we've already dealt with because we already know the answers. And the function I'm going to look at next is the square root of x. So if you look at the square root of x here, f of x is the square root of x. We've been here before. In fact, we drew the square root of x curve, and actually the first area that we computed was this one up against the y-axis. And the only way to really do that, to get area up against the y-axis like that, is you need little slices of y, delta y's. We don't use height. We don't use y values for height. We actually use x values for height. So we did do this, and it was a little more difficult, but we got 1/3 over there. And then we got 1/3 here, and therefore it implied that the area beneath the curve was 2/3. That was the implication. We also used the limit method on getting the area beneath the curve, and we got 2/3. So we actually got 2/3 two different ways. Well, here comes the third method of getting that 2/3, at least we hope we get 2/3, and that is finding the area beneath the curve using the fundamental theorem of calculus. So the area ought to be the integration or antiderivative of the square root of x, plugging in the 1 and plugging in the 0 and subtracting those results. Well, before I can do that, I really ought to turn this into an exponent. So that's x to the 1/2. That antiderivative or integration symbol is staring down at that exponent, and you remember what it's going to do to it, right? Add 1 to the exponent, divide by the new exponent. So we get x to the 3/2 divided by 3/2. Well, before I plug the numbers in, because you notice I did put the numbers 0 and 1 over there, you'll notice also that I did not put a constant of integration. When you're doing a definite integral, where you have your upper and lower limits of integration, you don't need to write plus c anymore because they cancel out. So we saw that in the previous example. I put plus c and I got a minus c. I put a plus c2, I got a minus c2. They canceled out. So if you're doing a definite integral, there's no need to put plus c anymore. You still need the plus c for an indefinite integral without the limits of integration, in which you produce capital F of x. If you do that, you do need the plus c, and sometimes we can actually figure out what c is. But for a definite integral, c is irrelevant. Whether we know it or don't know it, it seems like it adds and subtracts and cancels out. So there's no need for that plus c anymore. I do see I'm dividing by a fraction, 3/2, so I flip the 2 up. It's a much better spot for the 2. That's where it belongs. What's next? We put the 1 into the problem. Stick the 1 in here. That's 1 to the 3/2. Minus, we stick the 0 into the problem. That's 0 to the 3/2, which zeroes out anyway. And we come to the same conclusion that we came to earlier. The area beneath the square root of x curved is 2/3. Okay, the next integral I'd like to look at, I want to now expand our horizons a little bit, and I'd like to be able to integrate and find the area beneath a more complicated curve, this parabola right here. 2x squared minus 4x plus 1. First thing I recommend, get your antiderivative, right? So let's get our antiderivative piece by piece here. The 2 is along for the ride, so we're not going to change that, but we are going to increase the exponent by 1. X cubed over 3, the new exponent. The minus 4, along for the ride. We're not going to change that, but x to the 1 becomes x squared over 2. And be careful, guys, because if you see that constant, some people are going to think 0, but that's for derivatives. I'm thinking of an original function whose derivative is 1. I'm thinking of x. So don't forget, that is an important component to this problem. Now, if you want to sweep out area from 1 to 4, we put our 1 and 4 at the back of this function to remind us that we need to plug it in. So let's plug in the 1 and the 4. So first thing I'm going to do is just simplify a little bit here. I noticed that I could simplify this term here, make that 2x squared, so I've got that out of the way. And now, plug in your numbers. So let's plug in our 4 here, our 4 here, and our 4 there. And then a big minus. The minus comes from the fundamental theorem of calculus. And then plug in your 1 into the function. Here, over there, I put my 1 in. So let's see what we get here. Ultimately, I'm getting, on the left side, this is 64 times 2, or 128. This is 16 times 2, or 32. This is just 2/3 minus 2 plus 1. So I propagate the minus sign through, distribute it through, and that changes all of my signs over here. First thing I noticed was I decided to get these two to go together because they already shared the same denominator. 128 minus 2 is 126. And then I just added these numbers together. These 4 numbers here made minus 27. Well, it turns out 126 over 3 is 42, and 42 minus 27 is 15. So the area beneath this curve from 1 to 4 is actually 15. I need you to be a little bit careful because you got a positive area, so you might think that all of the area lives above the x-axis because positive area supposedly lives above the x-axis. Might not necessarily be true. It means the majority of the area is above the x-axis. You very well, from 1 to 4, you might have 30 units of area above the x-axis, and then over here you have 15 units of area below the x-axis, and they go together and get you that 15. So just because the area is positive doesn't mean all of it lives above the x-axis. It means the majority of it. In this case, probably all of it. But just kind of thinking about that. In fact, since we are thinking about that, there are times when we get an area under the curve of 0. So I want to show you how that might happen. Take a look at the sine curve, for example. The sine curve, which looks like this, if I were to investigate my sine curve from 0 to 2 pi, you'll notice that the sine curve does have area above the x-axis. I would consider that to be positive space. And it also has area that lives below the x-axis, and in calculus we consider that area to be negative space. And if I were to represent the area as a definite integral, I would certainly represent it this way. The area is a sweeping out or continuous sum from 0 to 2 pi underneath the sine curve. So we sweep out area positive, but as we're accumulating area, we accumulate negative area. And ultimately, without having to do any math, I think you know the answer, it's 0. So they cancel each other out. Let's see if that holds true by actually doing the calculus. The antiderivative of sine is not cosine. Got to remember everything's backwards. It's minus cosine. And then you take your limits of integration and you plug them in. So 2 pi goes in and 0 goes in. So what we need is we need minus the cosine of 2 pi, and then fundamental theorem of calculus minus a minus cosine of 0. That's a double negative, which turns positive. So what is the cosine of 2 pi? Come on over to the cosine curve to realize that the cosine of 2 pi is 1. The cosine of 0 is also 1. And so ultimately I get minus 1 plus 1 is 0. So our suspicion about this area being 0 is certainly confirmed. Calculus is able to do that using the definite integral and the fundamental theorem of calculus. What that doesn't answer is the following question. If we go back to the top here, it doesn't answer how much area lives in this space here, or how much area lives in this space over here. Of course, I believe them to be exactly the same, with one being positive and one being negative, but I don't have any idea as to what that area is. Now, I can estimate that area, because if you draw a little box here, you have a pi by 1 rectangle. So the area of the rectangle is pi, which is roughly 3, but we didn't take all of that 3, so maybe it's around 2, you know? Now, the way to figure this out, in fact, what I'd love to see is I'd love to see area go negative, so I'm going to integrate the area from pi to 2 pi on the sine curve. And what I expect to get is a negative area, and I think it's reasonable to assume that it should be close to negative 2. Let's do it. Find the area beneath the curve up against the x-axis from pi to 2 pi on the sine function. The antiderivative of sine is minus cosine, no need for plus c anymore. And you plug in 2 pi in here, and you plug in pi in there. But you have to subtract the two results. So let's see what we got. So the first result is minus the cosine of 2 pi. You just inject 2 pi in there. Fundamental theorem of calculus says minus, that's plus now, cosine of pi. Well, take a look at what we have here. They don't cancel out. We've done the cosine of 2 pi before. It is 1, so this says minus 1. The cosine of pi, well, let's go take a look up here. It's right there. Cosine of pi is negative 1. So I've got negative 1 minus 1. I've got negative 2. So we were spot on. Who would have really known that it was exactly minus 2? But apparently it is exactly minus 2. So the area of 1/2 of a sine curve is 2. And then the problem is you have 2 on the top and then minus 2 on the bottom. That's why they canceled out. But it is interesting that when you integrate from 0 to 2 pi, they get the whole thing, all you get is the 0. You don't get the information about how much area you have from 0 to pi. You actually have to run that integral to figure that out. Okay, I've got another example I'd like to take a look at, and that is I'd like to get the area using an absolute value. So let's take a look at this. If I were to get the area beneath the curve, the absolute value of x minus 1, we'll struggle with this a little bit because you can't really integrate an absolute value. In fact, what you should do with an absolute value is break this function out as a piecewise defined function. Now remember, absolute value spends most of its life doing nothing. And the when, which goes over here, when does it use this? When does it do nothing? It does nothing when the contents are already positive. And of course, that's how we say positive in math, greater than 0. So apparently, when x is greater than or equal to 1, we should be using this function, which is just a line. But what about when x is less than 1? Well, when x is less than 1, the contents in here will be negative, and the absolute value kicks in and adds a minus sign. Now, when it adds a minus sign, it puts it out front, and you get a minus x and a plus 1. So I actually propagated that minus sign through so that you can see the function. Let's draw a picture of what's about to happen here in terms of getting area. So here we are at 1, 2, 3, and 0. So from 1 forward, we're supposed to use this line right here. So let's use it. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. Now, it is a linear function, so they better line up. And I have my ruler here so we can connect the dots. And they do line up, thankfully. Somewhat. Okay. So over here, we're supposed to be using this function when x is less than 1. So let's use that. Let's go here to x equals 1/2. If I plug 1/2 in here, I get 1 minus 1/2. I get 1/2. So that goes right about here. If I plug 0 in, I get 1 minus 0. I get 1. That goes here. So apparently over here on the left side, we get a negatively sloped line like this. So there's really two parts to this puzzle, and the first is on the left side here. Do we really need calculus to calculate the area of two triangles? I don't think we do. So let's do this, guys. Let's get the area of the first triangle. 1/2 base times height plus, let's get the area of the second triangle. 1/2 base times height. So area is 1/2. My base is 1. My height is 1. 1 by 1. Plus 1/2. My base is from 1 to 3. I guess my base would be 2. And my height is also 2. So let's add these together so that we can get our area underneath this curve. By the way, what's going on here? You got a sharp corner right there. Absolute values always seem to produce these sharp corners. And you know that it's non-differentiable right here at this point. In fact, the derivative is minus 1, minus 1, minus 1, minus 1, undefined. And then the derivative becomes 1, 1, 1, 1, 1 along that line right there. So just keep note that sharp corners should not have a derivative. It's non-differentiable at that point. This is 1/2 plus 2, because these two cancel. 2.5, or 5/2. So we represented the area using a definite integral first. Then we actually broke the absolute value into a piecewise defined function so I could see that sharp corner. And finally, I noticed that all I really needed was the area of triangles, and that's what I did. But let's see if we can do this with calculus. Calculus ought to give us the same result. So is it true that the area should be these two integrals? Let's start with this one here, because these are really different lines. So I want the area under that line, but only from 0 to 1. Now this line right here, this is the line minus x plus 1. Plus, now let's get the area beneath this line right here. So let me label these functions so we know which one we're using. This is the x minus 1 line, and this is the minus x plus 1 line. So now let's get the contribution of area from this. And the definite integral looks like this. We pick it up at 1. We continue out to 3. We sweep out area beneath the x minus 1 curve. Hopefully, the calculus works here and gets us that same exact area. So let's see if it does. Now let's do our anti-differentiation here. minus x becomes minus x squared over 2, plus 1 becomes plus x, and I'm supposed to plug in 0 and 1. Over here, I get plus x squared over 2 minus x, and I'm supposed to plug in 1 to 3. So yes, this one definitely breaks into two different definite integrals. So let's plug in our 1 first. We get minus 1/2 plus 1. Fundamental theorem of calculus says minus, now plug the 0 in, and I get 0 over 2 plus 0. No contribution from that one. Over here, you plug the 3 in. That's 3 squared over 2 minus 3, and then minus, that's the fundamental theorem of calculus, says subtract. Now plug the 1 in, and I get 1/2 minus 1. So we hope all that tallies up to 5/2. So what do we got here? This is worth 1/2. Plus, this is worth 9/2. Minus 3, minus 1/2, and then plus 1. Well, this is 10/2, and this becomes minus 2. That's these two together, and then minus 1/2. And so ultimately I have 5, basically minus 2.5, which is 2.5. So it worked with calculus as well. So that's something we had to break up. We had to break it up into two different integrals. And when we looked at the properties of definite integration, we found that we could actually do what we just did there, which is pause. You can integrate from 0 to 1, pause, and then pick it up from 1 to 3 on. And that's what we did. But at that pause, we actually had to switch functions, and that we did that, and we effectively got the same answer. Now, I want to show you really probably the last topic for this particular section, which is called the mean value theorem for integrals. It's a pretty powerful theorem, and what it allows you to do is calculate the average y value for a function. Now, for a discrete number of entries, like exam grades, finding an average is not a big deal. If you had 5 exams, you would add them all together, 1 through 5, get a number, and then divide by 5. And that's your average. But if you're trying to average values on a curve in a continuous fashion, how do you do that? Let me give you an example. Here's one 24-hour period, one day, and up here I'm going to track temperature. And what happens is the temperature starts off cool, peaks out for the day here, and then maybe drops down at night, like that. Now, what's the average temperature? The problem is, how do you average a continuous curve like that? Think of how many data points you have. They're not individual data points. It's a smooth, continuous flowing curve. How many points do you really have? You have an infinite number of data points, an infinite number of temperatures. So how do you add an infinite number of temperatures and then divide by infinity? You can't do that. So another idea might be that, all right, well, average temperature is probably going to be somewhere in the middle here, maybe right here, okay? Now, the interesting thing about selecting your average temperature is that what it does is literally form a rectangle. It forms a rectangle. There are 2 areas on the page now. There's this area here, which is the area of the rectangle. And then there's this area, which is the area under the curve. Here is the interesting thing about finding the average temperature or the average y value. And let's switch to x's and y's. If this is A, and this is b. It turns out that the area of the rectangle using the average y value is equal to the area under the curve. It's a pretty dramatic result. The area of the rectangle and the area of the curve should be a match. So I guess what you can imagine is calculate the area beneath the curve. We can do that with calculus. And then move that y-average up and down until you finally get a rectangle whose area matches. Let's finish this equation. What is the area of the rectangle? Well, take a look what it is here. It's the average, well, instead of t, we'll use y. It's the average y value times this master width. There it is, width times height. Well, the master width is b minus a. What is the area beneath the curve? We have a formulation for that. It's the definite integral. So it's only because you have the capacity for calculating the area under the curve that this works or makes any sense to us. Now I can actually determine the average y value. And it's as simple as this. If you want the average y value, then let's just divide by b minus a on both sides. So what's the average y value of a function between a and b? Well, first of all, it's the area underneath the curve from a to b, simply divided by the interval width. It's that one last component that turns it into an average y value, turns it from an area into something even more useful, which is an average y value. Let's do a problem and see if we can get the average y value for a particular curve. So I'm going to look at one of these examples here. Let's look at example 4. Example 4 has a function which is 3x squared minus 2x. They give us a graph so they can show us what the function looks like, and therefore we can get a reasonable idea as to what we think the average might be. And we're going to do this average just between 1 and 4. Okay? Now the first data point would be 3 minus 2, which is 1. But I'm actually going to have to change my axis considerably here because we're going to go all the way up to 40. So actually, if you put a 4 in here, you would compute y value 40. If you put a 1 in, you compute y value 1. And let's see, if we put a 2 in, we're going to get 12 minus 4 is 8. And so the curve comes up and looks like this. So the question is the average up here, right in the middle at 20, or down here closer to these values? And the answer to that question is this: where does the curve want to spend most of its time? And it has a little bit to do with concavity, if you take a look at it. This curve is concave up. In other words, it's trying to spend most of its time down here, and then finally it shoots up. Now, if it was concave down, it would shoot up and spend more time with higher y values. So this concave up nature weights the average down a little bit. I believe the average should be less than the middle or 20 because it's weighted down by the concavity of the curve. It spends most of its life a little bit on the low side. So what we're going to do is calculate the average y value, and let's see if it really is, as we expect, to be a little bit below 20. Now the average y value should be the area beneath the curve from 1 to 4, and here's the area represented as a definite integral, divided by the interval width, which is 4 minus 1. Don't forget to put this down here if you're doing an average y value. Let's do our Antiderivative up there, that's 3 x cubed over 3 minus 2 x squared over 2, and that's supposed to be run from 1 to 4. And when you're done, divide that whole result by 3. Well, these cancel and these cancel, so it makes it a little easier. I guess you can include the divide by 3 in there or not. It doesn't really matter. I seem to have put it inside, and that's okay too. So 4 goes in, and you get 4 cubed minus 4 squared all over 3. And then minus, now the 1 goes in, and you get 1 cubed minus 1 squared all over 3. Well, that is interesting because that's worth 0. 1 minus 1 is 0. So it's really over here. Well, you can compute this however you like, but if you factor out the 4, you get, 4 squared can be factored out. Let's take a look at that. Now I have 4 squared. I pulled the 4 squared out, leaving a 4 behind. I pulled the 4 squared out, leaving a 1 behind, all over 3. That's 4 squared times 3 over 3, or 4 squared, or 16. So our expectations were matched because we got something that was a little less than 20, was slightly weighted down by that concavity. So that's something interesting to note. If you look at a curve, you can ask this question. You can say, all right, well, first of all, the middle y value between maybe the top and the bottom is not really the average for this particular function, because if it spends most of its life lower, it's going to weight the average down. If it shoots up fast, then it's going to spend most of its time at higher y values, and it will be higher than just adding the max and min y value and dividing by 2. So that's something that was realized by this particular problem. Definitely encourage you to now practice by doing the antiderivative, doing definite integration, and plugging your limits of integration in very carefully, subtracting the 2 always, and now you know that you don't need plus c anymore. The plus c is reserved for indefinite integrals in which you spell out the antiderivative function. You don't need it for definite integrals, and that's a good thing. If you put plus c in, you're not wrong necessarily, but they will cancel, so there's no need for it. Thanks very much. Good luck working on some homework. Send me questions if you have any questions. Thanks.